Welcome to Pendekatan channel. In this occasion, we're going to discuss about the following theorem, which says that A is normal matrix, if and only if A is unitary diagonalizable. So let us recall what is a normal matrix. A is a normal matrix if A star is equal to A star A. And the A star here is the transpose conjugate of matrix A. And then the next definition is, we call that A is unitary diagonalizable if there is a unitary matrix U and a diagonal matrix D such that U times A times U star is equal to D. Alright? So let us start. So let's find out in which direction it is easier to prove. Okay, to prove that something is normal is quite easy. We need to check whether this equation holds true. Okay, so we're gonna just do in that direction first. We're gonna do from right to left direction. Okay, so suppose that A is unitary diagonalizable. So it means that A can be written as U star D times U. Okay, and then from this, if we star this A, it follows that we have A star is equal to U star D star U. And if we have a diagonal matrix and then we take a transpose conjugate of that matrix, then what we do is basically simply taking the conjugate of the diagonal entries. So we can write down D star as D bar, meaning that we conjugate each of the entry of D. Okay, so by having this, if we do A star, we're gonna have U star D, and then this U and those U star, by the definition of unitary matrices, we have U star is equal to identity matrix, so we're left with U star D bar U. And then if we do in the other direction A star A, then we will have U star D bar D U. Okay, but U star and U are well, actually you already see that they are equal, so we are done. Hence A is normal. Hold on, I need to say that because D times D bar is just multiplying the diagonal entry entry by entry, like for example, this is a very simple illustration. If you have something like this, two diagonal matrices, then when we multiply, we just multiply the non-zero entries, the diagonal entries. It's going to be AC and here is BD. Okay, so the correct word that I'm looking for is that diagonal matrices are commutative. So D bar is equal to D bar D. Hence A times A star is equal to A star times A. Since diagonal matrices are commutative, commutes when we multiply any two diagonal matrices, then we can multiply in any order we want. Okay, so here is the proof of from the right to the left direction. Okay, so the next one is we're gonna prove from left to right, and this is a little harder than the previous one. We're gonna use an induction, and for the base case we do for n equals 2. Okay, first pick an eigenvector u of a correspond to the eigenvalue lambda. This is eigenvalue. Okay, and then we can assume that this u is a unit vector. Without loss of generality, u is a unit vector. What I'm trying to say that we can find a unit vector u that having lambda as its eigenvalue. So u is the eigenvector of lambda. The eigenvector corresponds to lambda. Okay. And then we can complete this u, extend this u, so that we have take v, so that uv is an orthonormal basis. And why we can always do that? Orthonormal basis in C2. Okay. So remember that if we have a linear independent set, we can always extend it and then to make it into a basis. Okay. So now observe that if we multiply A, so this A is 2 by 2 matrix, and then we multiply with u times v. Okay. And then we want this to be our unitary matrix. So because uv is an orthonormal basis, then this matrix is unitary. Okay. And then we want A times u is equal to u times some diagonal matrix. Okay. So hold on. This one is okay, let's call this as u. So call this q. Okay. And then we need to find out what should we multiply here in order to get this expression. So let's do it here. A times u is a u, a times v is a v. But a u, because u is an eigenvector of a correspond to lambda, this is equal to lambda u, and this is a v. On the other hand, lambda u can be obtained by multiplying u with the vector lambda 0. So if we multiply u with the vector lambda 0, we exactly get lambda u. And then in order to get a v, we just multiply here with u inverse a v. Okay. So Okay, so we have this identity that lambda u lambda the matrix where the first column is lambda u and the second column is AV is the same as the product of these two matrices. Okay, so to make this expression easier, okay, we will rewrite this as, so AU is equal to U lambda 0, and then this is just any vector. I mean, we can replace this as, let's say this is as alpha beta, some vector in C2. Okay, and then we want to justify that if we have this equation, it turns out that the value of lambda have to be 0, and therefore we can diagonalize A. So our objective is that from this equality we would like to have that alpha is equal to, this is alpha is equal to 0. So you can write this A as U lambda 0 alpha beta U star, and using the assumption that A is normal, then we have A star times A. So if we do A star, we have U, and then the star of this, which is lambda star alpha star, and then 0 beta star, sorry, beta bar, and then U star. This is our A star times U alpha 0, sorry, lambda 0, lambda alpha 0 beta U star. And if we simplify this, we get U times lambda star lambda, and then lambda star alpha, and then alpha star lambda, and the last one is lambda star lambda plus beta. I'm sorry, again, this should be, well, this is the same thing as star actually, but the proper way is this, the conjugate B star beta bar beta. Okay, and that is the A star A. And then if we reverse the position, so if we do U alpha, I'm sorry, lambda alpha 0 beta U star U alpha bar beta bar U star, this is identity. So if we multiply this and that column, we have lambda star. Well, actually the important part is the last entry, I mean the corner entry here. This is U star. Okay, over here we have beta star, beta bar. Okay, so we can cancel, because the two are equal, we can cancel the U and the U star here and there, and therefore we can conclude that this must be equal to that. And the only way to have these quantities to be equal is when alpha equal to 0. So therefore alpha equal to 0, because this yeah, both of them, I mean, from this equation we have alpha bar alpha is equal to 0, but this one is the modulus of alpha squared is equal to 0. This can only happen, which implies alpha is 0. Okay. So if alpha is 0, then we have A is equal to U lambda 0 beta U star, which means that A is diagonalizable by this exact u. Okay, so A is unitary diagonalizable, is unitary diagonalizable. Okay. Okay, that's only for n equals 2. We need now to generalize this argument, but somehow the argument is similar to what we just did. Okay. So now for general n, we assume that the result holds for n minus 1, meaning that if we have any normal matrix of size n minus 1 by n minus 1, then that matrix can be unitary diagonalizable by n minus 1 times n minus 1 unitary matrix. Okay. So now we're gonna repeat the argument. We claim that there is y star and b such that a times u is equal to u lambda 0 y bar and then b. So this b is a matrix of size n minus 1 by n minus 1. And it follows that this y star is a row vector, a matrix of size 1 by n minus 1. So, okay, we claim that we can write a u as u times this for some y star and b. Okay, how we do that? It is similar to what we just did. So to do this, to do the above, take the columns of u to be orthonormal basis of A, where the first column of this capital U is the small u that we have in the earlier case. Well, I mean, we can pick an eigenvector u also in the case in general n. So, okay. So this lambda is still the eigenvalue of our eigenvector u. So take the columns of u to be orthonormal basis of A with little u as its first column. Okay, so our u is something like this is u and then some bunch of column vectors. Let's all of them, we call it as C. Okay, capital C. Okay, so then if we look at this, the first column of the left hand side is already matched with the first column of the right hand side, because u times the vector, the column vector lambda 0 is exactly lambda multiply by scalar lambda is multiplied to the first column of u. So this is exactly the same. So in order the second column to be the same, then we put this as, so in order to have A times C, then here we just need to put it as U inverse times A times C. Okay, and then we write down this U inverse AC as Y star P. Okay, we can always do this. Okay, so therefore we have AU is equal to U lambda Y star 0 P. Okay, now using similar argument, so here we have A is equal to U lambda Y star 0 P U star. Remember that A is normal, so since A is normal, we can multiply this A with A star, and then we compare with A star times A. So from that equation that A star times A is equal to A times A star, so let's do this. For example, A star is equal to A star A. So then we will have lambda Y bar 0 P, and then lambda star, let's become Y, and then 0 B star is equal to the other way around. Okay, the left hand side gives us lambda star. Meanwhile, the first entry of lambda bar plus Y star Y, and then the first entry here we have lambda star, lambda bar lambda. So just looking at the first entry only, we can conclude that Y star Y is equal to 0, meaning that Y is 0. Okay, and then we have P star, and over there, since Y is equal to 0, we have, I'm sorry, this should be B star B. Okay, so we also conclude that B is normal. Okay, so by using assumption that we can have this kind of equation, by using the normality of A, we conclude that Y is equal to 0, and B is a smaller size normal matrix. Okay, now we can use the induction hypothesis. Because B is normal, then according to the hypothesis, we can diagonalize B. Okay, so let V diagonalize B, meaning that what? That B is equal to some V D1 V star. Okay, V unitary, and then D1 diagonal, both in both are matrices of size n-1 by n-1. Okay, now somehow in order to diagonalize A, we need to use this D1 and this alpha. Okay, so let's rewrite this as follows. So AU is equal to U lambda y star. Remember the y star is 0, so this is just 0, 0, and then our B is exactly V D1 V star. Okay. But this can be written as U 1 0 0 V times lambda 0 0 D1 times 1 0 0 V star. Okay. Or if we multiply with the inverse of this, we have AU 1 0 0 V is equal to U 1 0 0 V times this. This is our diagonal matrix. And then we can call this as W, for example. And since U unitary, this is also obviously unitary, therefore W is unitary. Therefore, we can have A is WD W star. Therefore, A is normal. Alright, so that's it. So we know that the normality of a matrix is equivalent with the fact that A can be diagonalizable, can be diagonalized unitarily. Okay, thank you for watching. See you again next time on the next video. Okay, don't forget to subscribe to the channel. See you again. Bye bye.